Imagine standing on a boat in the middle of the South Pacific. The water looks calm, blue, and harmless, like it is trying very hard to keep a secret. Beneath that gentle surface, however, the earth suddenly gives up on subtlety. The seafloor does not slope downward politely. It vanishes. The Tonga Trench is a colossal scar in the planet's crust, plunging downward for more than 10 kilometers. If Mount Everest were dropped into it, the peak would still be underwater, quietly regretting its life choices. This trench stretches like a dark slash along the edge of the Pacific Plate, marking one of the most dramatic drop-offs on Earth. It is not just deep, it is aggressively deep. This is the kind of place where sunlight gives up long before the halfway point, and pressure builds layer by layer until it becomes the dominant law of reality. Whereas down here, physics is not a suggestion. It is a strict manager with a clipboard. As we descend in our imagination, the water grows colder, darker, and heavier. The pressure increases so fast that every square inch of anything down here is being squeezed by the weight of entire skyscrapers made of water. This is why scientists cannot simply swim down and take notes. Human bodies are fantastic at many things, like storytelling and making snacks. But surviving crushing pressure is not one of them. Even our best technology approaches the trench with the caution of someone tiptoeing past a sleeping dragon. If this calm dive into what scientists continue to find inside the Tonga Trench helps you unwind tonight, please like the video, subscribe to the Deep Sea documentary channel, and leave a comment sharing when and where you're listening. And so this slow science can reach more people who fall asleep to the deepest parts of the ocean. The Tonga Trench feels less like a place and more like a boundary. It marks the edge between what feels familiar and what feels alien, even though it is right here on our own planet. It is one of those locations that reminds scientists just how thin the layer of comfortable Earth really is. We live on the skin of a world that gets weird very quickly once you peel back the surface. What makes the trench especially captivating is how quiet it is. No waves, no wind, no sound, except the occasional low rumble transmitted through rock and water. It is not empty silence either. It is a kind of heavy silence, the kind that presses in on you, as if the ocean itself is listening. The trench does not feel hostile in an obvious way. It feels indifferent, which is somehow more unsettling. For scientists, this is part of the allure. The Tonga Trench represents one of the last places on Earth where the rules feel different enough to challenge our assumptions. It is a reminder that the planet does not revolve around us, even if we occasionally behave like it does. Down here, human timelines, human senses, and human expectations lose their authority. The trench has been doing its thing for millions of years, whether we are watching or not. There is also something deeply humbling about realizing how little of this place has been seen. We have detailed images of distant galaxies, yet vast stretches of this trench remain completely unobserved. It is like owning a house where one entire room has been locked for centuries, and instead of checking it, we decided to build telescopes. The Tonga Trench is Earth's locked room, and scientists are still fumbling for the key. The scale alone messes with your brain. The trench is not just a hole. It is a massive geological feature shaped by the slow, relentless movement of tectonic plates. These plates slide, collide, and sink with a patience that makes human projects look impulsive. While civilizations rise and fall on the surface, the trench continues to deepen and evolve, carving itself into the planet with quiet determination. And yet, despite its depth and darkness, the Tonga Trench is not a dead zone. That idea, that the deepest parts of the ocean are empty voids is one of the myths scientists have had to unlearn. The trench is not a graveyard. It is more like a hidden city, operating on rules that feel bizarre from the surface but make perfect sense down below. Life, as chemistry and geology, all intersect here in ways that challenge what we think is possible. Standing at the edge of the trench, even metaphorically, forces a kind of perspective shift. It reminds us that Earth is not finished revealing itself. There are still places that feel untouched, still environments that refuse to be easily explained. The Tonga Trench is one of those places where curiosity outweighs fear, even when fear is completely reasonable. This is where our journey begins. Not at the surface, where things are familiar and forgiving, but at the edge of a plunge so deep it rewrites the rules. The Tonga Trench is not just a destination. It is an invitation to rethink what our planet is capable of hiding, and what it might still be willing to show us, if we are brave enough to look straight down into the dark. For most of human history, the Tonga Trench was not so much a place as it was a rumour. Sailors crossed the Pacific knowing the ocean was deep. But deep is a wonderfully vague word. It could mean a few hundred meters, or an unfathomable abyss that eats ships for breakfast. For centuries, the trench existed only as a blank stretch on nautical charts, politely labelled with phrases that translated roughly to, "Here be water, lots of it." The first real attempts to understand depths like Tonga were almost charmingly primitive. Early oceanographers dropped weighted lines over the side of ships and waited, and waited, and waited some more. If the line kept sinking, they assumed the ocean floor was still on vacation somewhere far below. This method technically worked, but it was about as precise as measuring a skyscraper by dropping a rope and hoping it hits the sidewalk. In deep trenches, currents bent the lines, weights drifted, and the numbers came back with the scientific accuracy of a guess made before coffee. Everything changed when sound entered the picture. Scientists realized that instead of physically touching the seafloor, they could listen for it. Sound waves travel efficiently through water, and when they hit the ocean floor, they bounce back. By measuring how long that echo takes to return, researchers can calculate depth. This technique, known as echo sounding, was the oceanographic equivalent of turning on a flashlight in a dark room and finally seeing the walls. Early sonar systems were crude by modern standards, sending single pulses straight down and creating narrow depth profiles. They revealed that the ocean floor was not flat at all, but wrinkled, jagged, and dramatic. For the first time, scientists could confirm that trenches like Tonga were not exaggerations or cartographic mistakes. They were very real and very deep, and apparently uninterested in making things easy for humans. As technology improved, sonar evolved into multi-beam systems. Instead of sending one sound pulse downward, ships began firing wide fans of sound that scanned large swathes of the sea floor at once. This allowed scientists to create detailed maps that showed slopes, ridges, and sharp drop-offs in stunning clarity. The Tonga Trench emerged from the darkness as a massive, complex feature. Not just a single groove, but a dynamic landscape carved by geological forces over immense spans of time. Well, what makes this process especially fascinating is that scientists are mapping the seafloor without ever seeing it directly. The ocean is too deep and too dark for cameras during mapping missions, so everything is reconstructed from echoes. It is a bit like mapping your living room by shouting and timing how long it takes for the sound to bounce back. Except your living room is 10 kilometers underwater and actively trying to crush your equipment. The irony here is impossible to ignore. By the time detailed maps of the Tonga Trench were emerging, humans had already mapped the surfaces of the Moon and Mars with impressive precision. We had elevation models of alien worlds, while huge portions of our own planet remained blurry guesses. It is a strange realization that the place you might least understand is the one you are standing on. Our mapping the Tonga Trench also required patience on a heroic scale. Survey ships move slowly, tracing careful paths across the ocean to ensure coverage. Each pass adds another strip of data, gradually building a picture of the trench. There are no shortcuts. You cannot rush sound waves, and you cannot skip sections without leaving gaps in the map. It is meticulous work, the scientific equivalent of coloring inside extremely deep lines. Even with advanced sonar, the data is not perfect. Water temperature, salinity, and pressure all affect how sound travels, so scientists must constantly adjust their calculations. Raw sonar data looks messy at first, filled with noise and distortions. Turning it into a clean map requires processing, correction, and a lot of mathematical patience. The final images may look smooth and effortless, but they represent countless hours of careful refinement. What emerged from these efforts was not just a measurement of depth, but a new way of understanding Earth's hidden architecture. The Tonga Trench stopped being an abstract extreme and became a defined structure with contours and personality. Scientists could see how steep its walls were, how narrow some sections became, and how abruptly the seafloor dropped away. The trench transformed from a mystery into a subject that could be studied, debated, and explored further. There is something quietly profound about this achievement. No dramatic explosions, no flag planting, just sound waves, patience, and curiosity, slowly revealing one of the most inaccessible places on Earth. Mapping the Tonga Trench did not conquer it, it introduced it. And in doing so, it reminded us that exploration is not always about going somewhere new. Sometimes it is about finally paying attention to what has been beneath us all along, waiting patiently in the dark, while we were busy looking up at the stars. Depth in the ocean is not just a number. It is an experience, even if no human can directly have it in the Tonga Trench. As you move downward through the water column, something invisible but relentless begins to pile up above you. Every meter adds more weight, more force, more insistence that space itself should be smaller. By the time you reach the depths of the trench, the ocean is no longer just water. It is a crushing presence, pressing in from every direction at once. Pressure increases steadily as you descend, and by the time you approach the bottom of the Tonga Trench, and it reaches levels that defy everyday intuition. Imagine stacking the weight of dozens of commercial airplanes onto an area the size of your thumbnail. Now imagine that pressure being applied evenly, constantly, without relief. This is why the trench is not merely deep. It is fundamentally hostile to anything built for the surface world. Water is famously incompressible, which means it does not politely squish out of the way when more of it is added. Instead, it transfers its weight directly to anything below. At extreme depths, this turns the ocean into something that behaves less like a fluid and more like a solid wall. Materials we consider strong at the surface, like steel and glass, suddenly seem fragile. Structures that are slightly flawed or poorly designed do not fail slowly. They fail instantly, collapsing inward in fractions of a second. This pressure changes the rules of matter itself. Gases cannot exist in open spaces the way they do near the surface. Air pockets disappear, crushed into nothing. Objects filled with air, like plastic bottles or hollow shells, implode dramatically. The deeper you go, the more the ocean insists that empty space is unacceptable. Down here, everything must be dense, compact, and ready to be squeezed. For humans, this environment is hilariously unforgiving. Our bodies are mostly water, which sounds promising at first, until you remember the inconvenient presence of air-filled spaces like lungs, sinuses, and ears. These spaces would collapse almost immediately under trench-level pressure. The result would not be dramatic or cinematic. It would be fast, final, and deeply incompatible with survival. While the soda can analogy is generous, a better comparison might be a grape meeting a hydraulic press, even objects without air struggle. Pressure affects chemical bonds, altering how molecules behave. Some materials become more brittle, others warp. Electronics stop functioning properly unless specially protected. This is why exploring the Tonga Trench requires equipment designed not just to survive pressure, but to embrace it. Everything must be sealed, reinforced, and tested against forces that no surface environment ever produces. One of the strangest aspects of extreme pressure is that it is perfectly uniform. It does not push from one side or another. It pushes from everywhere at once. There is no direction to escape. This makes it uniquely challenging for engineers, because even tiny weaknesses become catastrophic. And a microscopic crack is not a minor flaw at depth. It is an invitation for the ocean to rush in and take everything with it. Pressure also affects temperature in subtle ways. While the deep ocean is cold, the compression of water and materials creates conditions where thermal behavior changes. Heat does not dissipate the same way it does near the surface. Equipment can overheat internally, even in near freezing water, trapped inside protective shells that must be thick enough to resist collapse, but thin enough to release heat. Designing for this environment is a balancing act between strength and functionality. What makes the Tonga Trench particularly fascinating is how stable these crushing conditions are. Once you reach a certain depth, pressure does not fluctuate much. There are no storms, no waves, no tides strong enough to matter, as the environment is brutally consistent. This creates a world where survival depends entirely on being built for permanence. There is no room for flexibility or improvisation. This constancy forces scientists to rethink assumptions about what materials can do and how structures should be designed. Concepts that work beautifully on land fail spectacularly here. Hinges, joints, and seals all behave differently. Even lubricants can solidify or behave unpredictably. Every component must be reconsidered from the ground up, because the ground itself is pressing upward with unimaginable force. Understanding this pressure is not just about satisfying curiosity. It reshapes how scientists think about extreme environments in general. The Tonga Trench becomes a natural laboratory for studying how matter responds when pushed to its limits. It reveals vulnerabilities in materials and designs that would never appear under normal conditions. In that sense, the trench is less a place and more a stress test created by the planet itself. Standing at the surface, it is easy to forget that the ocean is stacked vertically, layer upon layer, bearing down on the depths below. The Tonga Trench is where that weight finally becomes overwhelming, where the ocean stops being a backdrop and becomes the main character. Down there, pressure is not just a feature of the environment, it is the environment, and it serves as a constant reminder that Earth has ways of humbling us that do not require fire, wind, or shaking ground, just the quiet, patient weight of water, doing what it has always done, one crushing layer at a time. For a long time, scientists assumed that the deepest parts of the ocean were biological dead zones. The logic seemed sound. No sunlight, crushing pressure, near freezing temperatures, and very little food, do not exactly scream thriving ecosystem. The deep trenches were imagined as empty pits, where life simply gave up and turned around. Then scientists actually looked, and the trench responded by politely proving them wrong. When the first cameras and sampling devices reached extreme depths, they did not return with images of lifeless mud. They returned with movement, shapes, creatures calmly going about their lives in a place that should have been uninhabitable. It was one of those scientific moments where the universe clears its throat and says, "You might want to rethink that assumption." One of the earliest surprises came in the form of amphipods. These small, shrimp-like crustaceans were found in abundance at trench depths, scuttling across the seafloor like they owned the place. Amphipods are scavengers, and in the trenches they have evolved into versions that look sturdier, larger, and slightly more intimidating than their shallow water relatives. They are built to endure pressure and make the most of whatever food drifts down from above. In a world of scarcity, they have mastered the art of being opportunistic. Amphipods in the Tonga Trench are not just surviving, they are active, mobile, and surprisingly numerous. Their bodies are flexible rather than rigid, allowing them to withstand pressure without snapping or collapsing. They move with an energy that feels almost defiant, as if to say that environmental limits are more like suggestions if you are determined enough. And then there are the snailfish, perhaps the most unexpected residents of the deep. These fish are delicate looking, with translucent bodies and soft, gelatinous flesh. At first glance, they look like something that should not exist at all, let alone at the bottom of one of the deepest trenches on Earth. And yet, here they are, calmly swimming through the darkness like it is no big deal. Snailfish lack the heavy bones and rigid structures we associate with fish. This is not a design flaw. It is a survival strategy. Hard bones are a liability under extreme pressure, prone to stress and fracture. By reducing bone density and increasing flexibility, snailfish avoid being crushed. They are living proof that sometimes the best way to survive intense pressure is to stop resisting it and just go with the squeeze. Beyond amphipods and snailfish, and if scientists have identified a variety of other organisms adapted to trench life. Worms burrow through sediment, processing organic material in slow, efficient ways. Sea cucumbers glide across the seafloor, vacuuming up nutrients like biological Roombas that never need recharging. Each organism fills a specific role, contributing to a surprisingly organized community operating in perpetual darkness. What unites these creatures is not just their location, but their biology. Life at extreme depth requires fundamental changes at the cellular level. Proteins must remain stable under pressure. Cell membranes must maintain their structure without becoming rigid or leaky. Metabolism must be efficient enough to function with limited energy input. These are not minor tweaks. They are deep evolutionary commitments. One of the most fascinating aspects of trench life is how calm it appears. There is no frantic movement, no constant struggle. Energy is precious, so everything happens deliberately. Creatures move slowly, feed carefully, and waste nothing. It is a world built on efficiency rather than speed, where patience is rewarded and excess is punished. This discovery of life forced scientists to confront an uncomfortable truth. Our definitions of habitable environments were too narrow. We had assumed that life required conditions similar to our own, but the trench revealed that life is far more flexible than we imagined. It can adapt to darkness, pressure, and scarcity in ways that feel almost creative. There is also a strange familiarity to trench ecosystems. Despite the extreme conditions, they still follow recognizable patterns. There are scavengers, predators, and organisms that recycle waste. The roles are familiar, even if the players look like they were designed by someone who enjoys unsettling art. This suggests that life, once it gains a foothold, tends to organize itself in predictable ways, no matter how strange the environment becomes. Finding life in the Tonga Trench did more than add new species to scientific catalogues. It reshaped how scientists think about the resilience of biology itself. If life can flourish here, under pressures that crush steel and in darkness that never ends, then the boundaries of possibility are far wider than we once believed. In the end, the creatures of the trench are not just curiosities. They are quiet reminders that Earth does not revolve around human comfort. Life does not wait for ideal conditions. It adapts, improvises, and persists wherever it can. And in the deepest, darkest parts of the Tonga Trench, it does so with a calm confidence that feels almost smug, as if the ocean is gently laughing at our assumptions, while its strangest residents go about their ancient, pressure-proof lives. If you were designing a fish to survive in the deepest parts of the ocean, you probably would not sketch something that looks like a translucent blob with a permanent expression of mild confusion. And yet, that is exactly what trench snailfish look like. And it turns out, they are absolutely winning at life down there. These fish are not evolutionary accidents. They are masterpieces of pressure management, shaped by an environment that rewards flexibility and punishes rigidity without mercy. At first glance, snailfish appear fragile. Their bodies are pale, almost see-through, with soft outlines that seem to blur into the surrounding water. Their fins are thin, their muscles understated, and their skeletons barely there. In shallow water, this would be a terrible idea. Predators would have a field day. But in the trench, where pressure dominates every interaction, this design is perfect. The absence of heavy, calcified bones means there is less internal resistance when the ocean presses in. Bones are wonderful for life on land and in shallow seas. They provide structure, leverage, and protection. At trench depths, however, dense bones become liabilities. They can fracture or stress under pressure, creating points of failure. Snailfish avoid this problem by keeping their skeletons light and partially cartilaginous. Their bodies behave more like soft frameworks than rigid machines, and allowing them to compress slightly without breaking. It is less stand your ground and more roll with the punch. Another critical adaptation lies in their tissues. Snailfish cells are rich in compounds that stabilize proteins under high pressure. Without these molecular reinforcements, the proteins responsible for basic biological processes would deform and stop working. Think of it as biochemical bubble wrap, protecting essential functions in an environment that is constantly trying to shut them down. These compounds are not optional extras. They are the difference between functioning biology and instant failure. Their muscles are also tuned for trench life. Snailfish are not built for speed. There is no point in sprinting when food is scarce and energy is precious. Instead, their muscles are efficient, allowing slow and controlled movements that conserve energy. Every flick of a fin is deliberate. Nothing is wasted. In the deep sea, being dramatic is expensive. Even their internal fluids are carefully balanced. The chemistry inside a snailfish helps equalize pressure between their bodies and the surrounding water. This prevents internal collapse and allows their organs to maintain shape and function. It is a delicate balance, one that surface animals could never manage without specialized evolution. Snailfish do not fight pressure, they match it. Their ghostly appearance is not just a side effect of these adaptations. Transparency can be an advantage in low-light environments, reducing visibility to predators. In the trench, where bioluminescence occasionally flickers like distant stars, blending into the darkness matters. And a translucent body does not reflect much light, making snailfish harder to detect. They are the aquatic equivalent of stealth mode. Despite their odd looks, snailfish are not passive drifters. They are active predators, feeding on small invertebrates that live in the sediment. Their mouths are well adapted for suction, allowing them to snap up prey with minimal effort. It is an efficient strategy in a place where chasing food would be a terrible investment of energy. One quick gulp beats a long pursuit every time. There is also something oddly endearing about their expressions. Snailfish faces often appear slightly droopy, with downturned mouths and large eyes. They look perpetually unimpressed, as if living under extreme pressure has made them deeply tired of everyone's nonsense. This, of course, is just human projection, but it does make them feel oddly relatable. Who among us has not felt a little gelatinous under pressure? Studying snailfish has required scientists to rethink how they collect and observe animals from extreme depths. These fish do not survive being brought to the surface. The change in pressure is too sudden and too severe. Instead, researchers rely on cameras, traps, and careful observations made at depth. What we know about snailfish is pieced together from fleeting glimpses and preserved specimens that offer only partial clues. What makes snailfish truly remarkable is that they are not just surviving at the edge of possibility. They are thriving. They grow, reproduce, and carry out their life cycles in an environment that would destroy most forms of life in seconds. Their existence pushes back against the idea that there is a clear boundary beyond which life cannot function. In a way, snailfish embody the philosophy of the deep ocean. Success does not come from strength or speed, but from adaptability, from knowing when to let go of rigid structures and embrace a softer approach. In the crushing depths of the Tonga Trench, snailfish float calmly through the darkness, living proof that sometimes the best way to survive overwhelming pressure is to stop being hard, stop resisting, and accept that being a little ghost-like is a small price to pay for enduring where almost nothing else can. When scientists first began to observe the deepest parts of the Tonga Trench for extended periods, they expected isolation. A creature here, a creature there, or maybe the occasional lonely scavenger wandering across the mud like a forgotten extra in a nature documentary. What they found instead was structure, patterns, interactions. In other words, an ecosystem. Not a bustling coral reef, but a carefully balanced community where every meal mattered and every organism played a role. The earliest clues came from baited camera systems lowered to the trench floor. These devices were simple in concept. Drop food, turn on a camera, wait. What happened next surprised everyone. Within hours, the bait was surrounded. Amphipods swarmed in dense clusters, moving with purpose and urgency. They were not random visitors. They were specialists, tuned to detect rare food sources quickly and exploit them efficiently. This behavior revealed something important. For scavengers to respond so rapidly, there had to be a stable population already in place. They were not wandering in from distant regions. They lived here. And where there are scavengers, there is usually something else supplying the leftovers. As observations continued, scientists began to notice larger, more deliberate movements in the background. Predatory fish appeared, hovering at the edges of camera frames, waiting for the right moment. These predators were not chasing prey at high speeds. Instead, they relied on patience and timing, conserving energy while monitoring the activity around them. It was a quiet kind of hunting, perfectly suited to an environment where reckless movement could be fatal. The presence of predators confirmed that the trench was not just a dumping ground for organic debris. It was a functioning food web. Energy entered the system and moved between organisms and was recycled with remarkable efficiency. Every organism, from the smallest scavenger to the top predators, was connected by a shared dependence on limited resources. One of the most striking aspects of this ecosystem is how tightly it is regulated. Food in the trench is scarce and unpredictable, so waste is not tolerated. Scavengers consume nearly everything edible. What they cannot digest is broken down further by smaller organisms living in the sediment. Nothing lingers for long. In a place where energy is precious, leftovers are a luxury no one can afford. This efficiency extends to predator behavior. Trench predators tend to be opportunistic rather than aggressive. They target weakened or distracted prey, often scavengers already busy feeding. This minimizes energy expenditure and reduces the risk of injury. In the trench, a wound that would be minor at the surface could be a death sentence. So caution is built into every interaction. The ecosystem also shows signs of vertical connections. While the trench floor is isolated from sunlight, it is not completely cut off from the rest of the ocean. Organic material from above eventually finds its way down, introducing pulses of energy into the system. Trench organisms have adapted to take full advantage of these events, responding quickly and feeding intensively before returning to a slower, energy-conserving pace. Over time, these patterns revealed a surprising level of stability. Despite extreme conditions, the trench ecosystem does not appear chaotic. It follows rhythms dictated by resource availability and biological interactions. There are dominant species, supporting species, and roles that remain consistent across observations. This predictability suggests that once life adapts to extreme depth, it can establish long-term balance. Perhaps the most humbling realization for scientists was how familiar all of this felt. Strip away the bizarre appearances and extreme conditions, and the trench operates on the same fundamental principles as ecosystems everywhere else. Producers, consumers, and recyclers. Competition, opportunity, and survival. The cast may look strange, but the story is instantly recognizable. This discovery challenged the idea that complexity requires abundance. The trench proves that intricate ecosystems can emerge even when resources are scarce and conditions are harsh. In fact, scarcity may drive efficiency and specialization, leading to systems that waste nothing and function with elegant precision. There is also an unsettling comfort in knowing that predation persists even here. No matter how deep you go, the rules do not disappear. Something is always hunting. Something is always being hunted. The food chain does not end at the surface. It stretches all the way down, adapting itself to pressure, darkness, and isolation without missing a beat. In the end, the Tonga Trench ecosystem stands as a reminder that life does not simplify just because conditions are extreme. If anything, it becomes more refined. Every interaction matters, every calorie counts. And even at the very bottom of the ocean, nature continues its timeless routine, quietly proving that no matter where you are on Earth, dinner is always someone else's problem. The Tonga Trench may feel isolated, but it is not cut off from the rest of the planet. It does not generate its own food. There are no plants growing in the darkness, no sunlight to power photosynthesis. And yet, life thrives there. The reason is simple, if a little grim. Gravity never stops working. Everything that dies near the surface eventually starts the longest, slowest fall of its existence. This steady rain of organic material from above is often called marine snow, though it is less magical than the name suggests. It is made of tiny particles of dead plankton, fecal pellets, mucus, and fragments of larger organisms. Imagine the leftovers of the ocean, gently clumping together and drifting downward like dust in a quiet room. Except this dust is food, and it is on a journey that can take weeks or even months to reach the deepest parts of the trench. As these particles sink, they change. Some are eaten along the way by midwater organisms. Others break apart, dissolving into smaller pieces. By the time anything reaches the trench floor, it is usually unrecognizable, transformed into a fine layer of organic rich sediment. This is not a feast. It is more like a steady trickle of crumbs, delivered with frustrating inconsistency. Occasionally something larger makes the journey intact. The body of a fish, a squid, or even a marine mammal can fall into the depths, creating what scientists call a food fall. These events are rare, but when they happen, they are transformative. A large carcass becomes an oasis of energy, attracting scavengers from across the trench. For a brief moment, the slow rhythm of trench life speeds up as organisms gather to take advantage of the unexpected bounty. These food falls shape behavior. Trench organisms have evolved to detect chemical cues in the water, allowing them to sense when something edible has arrived nearby. Amphipods and other scavengers can appear surprisingly quickly, covering a carcass in writhing layers as they feed. It is not pretty, but it is efficient. In an environment where food is unpredictable, speed matters when opportunity knocks. Most of the time, however, life in the trench depends on the slow, constant drizzle of marine snow. This creates a system where energy input is low but continuous. Organisms adapt by slowing their metabolisms, growing slowly, and living longer lives. There is no rush when your next meal might be days or weeks away. Patience becomes a survival trait. The trench also acts like a trap. Its steep walls funnel sinking material toward the deepest point, concentrating organic matter in ways that flatter seafloor environments cannot. This makes the Tonga Trench a kind of collection basin where nutrients accumulate over time. It is one of the few advantages of living at the bottom of an immense underwater canyon. Once this material reaches the seafloor, it does not go to waste. Scavengers consume what they can. Smaller organisms process what remains. Microbes break down complex compounds into simpler forms, releasing nutrients back into the sediment. The entire system operates like a recycling plant designed by nature, with nothing wasted and no room for inefficiency. Well, what makes this buffet particularly unappetizing is the temperature. Near freezing conditions slow chemical reactions and biological processes. Digestion takes longer. Decomposition is sluggish. This means food lasts longer than it would in warmer environments, but it also means energy is released more slowly. Trench organisms have adapted to extract maximum benefit from every bite, no matter how bland it might be. There is something almost poetic about this arrangement. Life at the bottom of the Tonga Trench is sustained by the surface world, even though the two never meet. Sunlight fuels photosynthesis far above, creating organic matter that eventually drifts into darkness. The trench is the final destination of energy that began its journey in the sky. It is a reminder that Earth's systems are deeply connected, and even across vast distances and extreme environments. This process also reveals a quiet truth about the ocean. The deep sea is not a separate realm. It is part of a continuous cycle, linked to surface waters by gravity, chemistry, and time. What happens above eventually influences what happens below, even if the effects take years to become visible. In the end, the Tonga Trench survives on leftovers. Not scraps in the casual sense, but the byproducts of life happening elsewhere. It is Earth's cold pantry, stocked slowly and unpredictably, yet used with remarkable efficiency. And while the idea of dining on marine snow may not appeal to us, for the creatures of the trench, it is more than enough. It is proof that even in the most remote corners of the planet, life finds a way to turn falling crumbs into a sustainable, if deeply unglamorous, a feast. For a long time, scientists believed that the deepest ocean trenches were insulated from one very modern problem: us. These places were so remote, so hard to reach, and so completely disconnected from daily human activity that it felt reasonable to assume they were pristine. Then cameras came back from the Tonga Trench with something unexpected resting on the seafloor. Not a strange new species, not an exotic mineral, a piece of plastic. Humanity, it turns out, had beaten the scientists there. Plastic pollution in the trench is not dramatic in the way oil spills or floating garbage patches are. There are no swirling islands of trash or bottles clinking together in the dark. Instead, the plastic appears quietly, almost politely, scattered among sediments and rocks, candy wrappers, fibres, fragments of bags, small enough to miss at a glance, but unmistakable once you know what you are looking at. The deepest parts of the ocean had become the planet's most inconvenient lost and found. The question, of course, was how? How does a plastic bag used on land or near the surface end up more than 10 kilometers underwater? The answer is frustratingly simple. Plastic is incredibly durable and surprisingly mobile. Once it enters the ocean, it does not disappear. It travels. Currents carry it horizontally, while gravity and biological processes slowly pull it downward. Over time, even buoyant plastics can become waterlogged, colonized by microbes, or weighed down by particles, causing them to sink. Some plastic sinks gradually as it breaks into smaller pieces. Others hitch rides, and tiny fragments can become embedded in organic material or trapped in fecal pellets produced by marine animals. When those pellets sink, the plastic goes with them, effectively sneaking past layers of the ocean like contraband hidden in luggage. Eventually, some of it reaches the trench floor, where it settles in among the natural debris. What makes this discovery especially unsettling is not just that plastic is present, but that it is persistent. The deep ocean is cold and dark, conditions that slow down the breakdown of materials. Plastic that reaches the Tonga Trench is likely to remain there for a very long time. There is no sunlight to degrade it, no waves to break it apart quickly. The trench is less a graveyard and more a storage unit, quietly holding on to our mistakes. And scientists have also found plastic fibres in sediment samples taken from trench depths. These fibres, often originating from synthetic clothing, are microscopic but widespread. They are easily ingested by small organisms, entering the food web at its base. Once that happens, plastic is no longer just an environmental contaminant. It becomes part of the biological system, moving from one organism to another in ways that are still not fully understood. The presence of plastic in the trench forces scientists to confront an uncomfortable reality. There is no true away when it comes to waste. The ocean does not act as a magic eraser. It acts as a conveyor belt. The Tonga Trench, despite its remoteness, is connected to human activity through currents, gravity, and time. It is proof that distance does not equal protection. Yeah, there is a bitter irony here. The trench is one of the least explored places on Earth, yet it contains unmistakable evidence of our influence. We have left a footprint in a place most humans will never see. It is as if the planet itself is archiving our behavior, filing plastic artifacts alongside geological records that span millions of years. Future scientists may one day identify our era not just by chemical signatures, but by the sudden appearance of synthetic debris in the deepest sediments. What worries researchers most is not just the presence of plastic, but its unknown effects. Trench organisms evolved in environments free from synthetic materials. Plastic introduces new surfaces, new chemicals, and new risks. Sharp fragments can cause physical damage. Chemical additives can leach into tissues. As microplastics can accumulate in bodies in ways that are difficult to detect, but potentially harmful over time. And yet, the trench does not react dramatically. There is no visible collapse, no immediate disaster. Plastic simply becomes another part of the environment, quietly absorbed into systems that were never designed to handle it. This subtlety is what makes the problem so troubling. The impact is not loud. It is slow, persistent, and easy to ignore if you are not looking directly at the bottom of the world. In a strange way, finding plastic in the Tonga Trench tells us as much about ourselves as it does about the ocean. It reveals how thoroughly human activity has permeated the planet, reaching even the most inaccessible corners. We have managed to leave fingerprints in total darkness, under crushing pressure, but at the edge of what life can tolerate. That takes commitment, even if it is the wrong kind. The trench does not judge. It simply records. And right now, buried among the sediments and strange life forms, is a quiet reminder that our habits have depth. Literal depth. No matter how far down you go, it seems there is still a trace of us, floating gently to the bottom, proving once again that the most persistent species on Earth may not be the ones with gills or tentacles, but the ones who invented plastic and then forgot where they put it. When people imagine life in the Tonga Trench, they usually picture fish, crustaceans, or other creatures with recognizable shapes and faces. But the real heavy hitters down there are invisible. Microbes dominate the trench, quietly running the entire operation without ever asking for credit. If the deep sea had an Employee of the Month program, bacteria would win it every single time. Microbial life in the trench exists in conditions that would instantly disable most complex organisms. There is no sunlight, which means no photosynthesis. Energy is scarce, temperatures are low, and pressure is relentless. And yet, bacteria thrive. Not just survive, but actively grow, reproduce, and reshape their environment. They do this by using chemical energy instead of light, tapping into reactions that seem almost alien from a surface perspective. These microbes live in the sediments, in the water just above the seafloor, and even inside other organisms. They form the foundation of the trench ecosystem, processing organic material and recycling nutrients. Without them, nothing else down there would function for long. They are the quiet engineers of the deep, constantly breaking down complex compounds into usable forms. One of their most impressive abilities is pressure tolerance. At trench depths, pressure threatens to distort proteins and disrupt cellular machinery. Microbes counter this by producing specialized molecules that stabilize their internal structures. These molecules act like molecular braces, holding proteins in the correct shape, even when the environment is doing its best to crush them. It is biochemistry taken to an extreme, refined over millions of years of relentless testing. Darkness is another challenge microbes handle with casual indifference. While surface life relies on light to power food production, trench microbes exploit chemical gradients instead. They feed on compounds released from sediments, such as methane or other reduced chemicals, using them as energy sources. This process, known as chemosynthesis, allows life to flourish without a single photon of sunlight. It is a reminder that energy comes in many forms, and life is happy to use whatever it can get. Microbes also excel at patience. Their metabolic rates are often extremely slow, allowing them to survive long periods with minimal energy input. Some trench microbes may divide only once every several years. In a world where food is unpredictable, this is a winning strategy. Why rush when time is abundant and the environment is stable? Microbes treat the trench like a long-term investment, not a sprint. Another remarkable trait is their ability to form communities. Microbes rarely operate alone. They create complex networks, thus exchanging nutrients and waste products in tightly coupled systems. One species' waste becomes another's food, creating efficient cycles that minimize loss. These microbial partnerships are so effective that they can persist even when external energy input drops to near zero. Scientists studying these microbes often describe them as extremophiles, but from the microbe's perspective, the trench is home. It is the surface world that seems extreme, with its wild temperature swings, intense radiation, and unpredictable conditions. Down in the trench, things are stable, quiet, and dark. Perfect if you are a microbe that dislikes drama. What makes trench microbes especially fascinating is how ancient their survival strategies appear. Some of the biochemical pathways they use may resemble those of early life on Earth, years before oxygen filled the atmosphere and sunlight became the dominant energy source. In this sense, the Tonga Trench is not just a remote environment. It is a time capsule, preserving ways of life that date back to the planet's earliest chapters. Studying these organisms has practical implications as well. Their enzymes function under pressure and cold, conditions that break down most biological molecules. Understanding how these enzymes work could inspire new technologies, from industrial processes to medical applications. Once again, microbes quietly offer solutions while we are busy underestimating them. Perhaps the most humbling realization is how resilient these microbes are. While complex life struggles with environmental change, microbes adapt. They evolve quickly, diversify rapidly, and colonize almost any available niche. Mass extinctions that wipe out large organisms barely register at the microbial level. From their perspective, Earth's history is a series of minor inconveniences. This is why scientists often joke, only half seriously, that microbes would outlive us all. Remove humans, remove animals, remove plants, and microbes would carry on without missing a beat. The Tonga Trench is proof of that resilience. Even in the most extreme conditions on the planet, microbial life is not hanging on by a thread. It is deeply entrenched, efficient, and thriving. In the grand hierarchy of life, microbes are the true survivors. They do not need light, warmth, or comfort. They need chemistry and time. And the Tonga Trench offers both in abundance. While larger creatures capture our imagination, and it is the unseen microbial world that truly defines life at extreme depths, quietly reminding us that size and complexity are overrated when it comes to surviving on a planet that never stops testing its inhabitants. At the bottom of the Tonga Trench, beneath the strange creatures and drifting debris, lies something even more revealing than life itself. Mud. Not glamorous mud. Not the kind you track into the house. This is fine-grained sediment, quietly settling layer by layer, recording Earth's behavior with the patience of a very organized accountant. If the planet had a filing cabinet, the trench floor would be one of its most detailed folders. Every particle that settles into trench sediments carries chemical information. Bits of organic matter, minerals, and dissolved compounds become locked into the mud, at preserving a snapshot of conditions at the time they arrived. Over years, decades, and centuries, these layers stack up, forming a chronological record of carbon movement through the ocean. Scientists study these sediments because Earth, it turns out, never throws anything away. It just buries it and labels the date. Carbon is the star of this story. It moves constantly between the atmosphere, the ocean, living organisms, and the seafloor. When carbon-rich material sinks into the Tonga Trench, some of it becomes part of long-term storage. This process helps regulate the planet's climate by removing carbon from the active system and locking it away in sediments. The trench acts like a deep freezer for carbon, slowing its return to the surface world. What makes trench sediments special is how efficiently they trap material. So the extreme depth and low disturbance mean that once particles settle, they are unlikely to be stirred back into the water. There are no waves, no strong currents, and no burrowing animals churning things up at high speed. It is a calm environment, perfect for preservation. Each layer stays where it belongs, quietly keeping score. Chemical reactions continue, even after burial. Microbes in the sediment break down organic carbon, releasing some as gases and transforming the rest into more stable compounds. These reactions leave behind chemical signatures that scientists can measure. Ratios of different carbon forms tell stories about how much material arrived, how fast it was processed, and how much was stored long-term. It is forensic science, but for the planet. By analyzing these chemical patterns, our scientists can reconstruct past changes in the carbon cycle. They can identify periods when more carbon was being buried, often linked to changes in ocean productivity or climate conditions. The Tonga Trench becomes a historical archive, offering clues about how Earth responded to natural shifts long before humans started rearranging things at industrial speed. One of the more sobering realizations is that human activity is now leaving its own chemical fingerprints in these sediments. Changes in carbon composition reflect alterations in the global carbon cycle driven by increased emissions and land use changes. The trench does not care where the carbon came from. It records it anyway. Every extra molecule we add eventually finds its way into the system, and some of it ends up stamped into the mud. This is where the receipt joke becomes uncomfortably accurate. The planet is not losing track of what we emit. It is itemizing it. Scientists can see shifts in sediment chemistry that align with recent human history, compressed into layers that future researchers will read like a sudden plot twist. Earth's deep sea is writing footnotes to our actions, whether we intended to leave notes or not. The chemistry of trench sediments also helps scientists understand long-term stability. Carbon stored in these depths can remain locked away for thousands or even millions of years, depending on geological processes. This makes trenches important players in Earth's ability to regulate itself over long timescales. They are slow, steady, and reliable, the opposite of the rapid changes happening at the surface. What makes this especially fascinating is how subtle the signals are. There are no dramatic visual changes, no obvious markers. Just tiny shifts in chemical ratios that, when interpreted correctly, reveal sweeping stories about ocean circulation, biological activity, and climate trends. It is a reminder that some of the most important processes on Earth happen quietly, without fanfare. Studying these sediments requires careful sampling and analysis. Scientists must extract cores of mud without disturbing the layers, preserving the timeline intact. Each core is like a vertical history book, with the newest chapters at the top and the oldest buried far below. Reading it requires patience, precision, and an appreciation for how slowly the planet writes. In the end, the Tonga Trench teaches us that Earth is an excellent record keeper. It tracks carbon with meticulous care, storing evidence in places few will ever see. While we may forget what we released yesterday, the planet does not. It files it away, deep in the dark, waiting for scientists to come along and read the receipts. If the Tonga Trench were just deep and full of strange life, that would already be impressive. But it also happens to sit on one of the most geologically intense neighborhoods on the planet. This is not a passive hole in the seafloor. It is the surface expression of a colossal underground process where parts of Earth's crust are colliding, bending, and disappearing into the mantle like they are being slowly fed into a planetary paper shredder. The trench marks a subduction zone, a place where one tectonic plate is sliding beneath another. In this case, while an oceanic plate is being forced downward at an angle, sinking deep into the earth. This motion is not smooth or gentle. It is slow, relentless, and full of friction. Imagine trying to shove a massive slab of rock under another slab that really does not want to move. Now imagine that happening over millions of years. That is the Tonga Trench. As the descending plate bends downward, it creates immense stress within the crust. Rocks are pushed, stretched, and fractured far beyond what they experience anywhere near the surface. This bending is so extreme that it generates earthquakes at depths that would be impossible in most other regions. The Tonga subduction zone is famous for producing some of the deepest earthquakes ever recorded, originating hundreds of kilometers below the surface. Yes, these deep earthquakes are particularly fascinating because they challenge our understanding of how rocks behave. At such depths, temperatures and pressures should make rocks flow slowly rather than snap suddenly, and yet they do snap. Something about the conditions inside the subducting plate allows stress to build up and release violently. Scientists are still debating the exact mechanisms, but the trench has become a natural laboratory for studying how Earth breaks itself from the inside. Closer to the trench itself, the seismic activity reflects the constant struggle between plates. Stress accumulates as the plates lock together, resisting motion. When that stress finally overcomes friction, it is released in the form of earthquakes. These events reshape the seafloor, alter stress patterns, and sometimes trigger cascading effects throughout the surrounding region. The trench is not just a result of tectonic motion. It is an active participant in it. What makes the Tonga Trench especially dynamic is the speed of subduction. Compared to many other subduction zones, this one moves relatively fast. Faster motion means more frequent stress build-up and release, turning the region into a hotspot for seismic activity. Earthquakes here are not rare anomalies. They are part of the ongoing rhythm of plate tectonics, like the creaking of a house that is constantly shifting its foundation. This constant bending and breaking also affects the shape of the trench itself. The seafloor is not static. Over time, seismic events can steepen slopes, trigger underwater landslides, and rearrange sediments. The trench is continually being remodeled, and even if those changes happen on timescales that feel slow to us, what looks permanent from the surface is, in reality, under construction. Scientists monitor this activity using networks of sensors, both on land and in the ocean. By analyzing seismic waves, they can trace how energy moves through the Earth, revealing the structure of the subducting plate and the surrounding mantle. Each earthquake sends out signals that act like X-rays, illuminating regions we can never visit directly. The trench becomes a window into Earth's deep interior. There is something oddly satisfying about thinking of the planet using this region to relieve stress. The crust bends, stores energy, and then releases it in sudden jolts. It is Earth's version of squeezing a stress toy, except the toy is thousands of kilometers long and the consequences can ripple across entire ocean basins. The Tonga Trench is where the planet stretches its limits and tests its own materials. This seismic activity also plays a role in shaping the long-term evolution of the planet. Subduction zones recycle old crust back into the mantle, where it can eventually contribute to new crust elsewhere. The trench is part of this global conveyor belt, ensuring the Earth remains geologically active rather than frozen in time. Without places like this, the planet would be a very different, much quieter world. Standing back and looking at the big picture, the Tonga Trench is not just deep because of erosion or chance. It is deep because Earth is alive with motion. Plates move, forces build, and the surface responds by folding inward. While the trench is the visible scar of that movement, a reminder that beneath the calm surface of the ocean, the planet is constantly reshaping itself. So while life adapts and sediments settle quietly above, the ground below is anything but peaceful. The Tonga Trench marks one of the places where Earth shows its restless side, bending its crust, snapping under pressure, and reminding us that the planet is not a static stage for life. It is an active, shifting system, always working, always adjusting, and occasionally shaking itself just to make sure everything is still moving. From the surface, the ocean above the Tonga Trench can look deceptively peaceful. Blue water, gentle swells, the kind of scene that makes you think nothing important is happening below. But scientists know better. Beneath that calm surface, the seafloor is in constant motion, shifting, flexing, and occasionally lurching in ways that can send energy racing across entire ocean basins. Studying trenches like Tonga is one of the best ways scientists have to understand how earthquakes and tsunamis are born. One of the key insights trench research provides is how earthquakes actually deform the seafloor. When a large earthquake occurs along a subduction zone, it is not just shaking rocks. It is physically moving sections of the ocean floor up or down. Even a vertical shift of a few meters, spread across a large area, can displace enormous volumes of water. That sudden displacement is what sets a tsunami in motion, not the shaking itself. By studying the precise shape and structure of trenches, scientists can better understand where this vertical movement is most likely to happen. While some parts of a subduction zone are more prone to locking, storing stress, until it is released in a powerful event. Others slide more smoothly, releasing energy gradually. The geometry of the trench helps determine which behavior dominates, making detailed seafloor maps and measurements critically important. Sediments play a surprisingly large role in this process. The layers of mud and debris piled along trench slopes can amplify or dampen motion during an earthquake. In some cases, these sediments can act like lubricants, allowing plates to slip more easily. In others, they can behave more rigidly, increasing the likelihood of sudden rupture. Understanding how these materials respond to stress helps scientists refine models of earthquake behavior. Trench research also sheds light on underwater landslides, which can generate tsunamis independently of earthquakes. When steep trench walls become unstable, large sections of sediment can collapse and slide downslope. This sudden movement displaces water in much the same way as a fault rupture, creating waves that radiate outward. By identifying areas where sediments are prone to failure, scientists can assess additional tsunami risks that might otherwise be overlooked. Another major contribution of trench studies is improving tsunami modeling. By knowing the exact shape of the seafloor, researchers can simulate how tsunami waves will travel once they are generated. Trenches can influence wave speed, direction, and energy distribution, subtly steering tsunamis as they cross the ocean. These details matter when predicting which coastlines will be affected and how severe the impact might be. The data gathered from trench regions also feeds into early warning systems. Instruments placed on or near the seafloor can detect pressure changes associated with passing tsunami waves. These measurements help confirm whether a tsunami has been generated and how large it might be, providing crucial minutes of warning for coastal communities. The better scientists understand trench dynamics, the more accurate and reliable these systems become. What makes this research especially challenging is the timescale involved. Large earthquakes and tsunamis are rare events, occurring over intervals much longer than a typical scientific study. Trenches, however, preserve evidence of past events in their sediments and structures. By analyzing these records, scientists can reconstruct histories of ancient earthquakes and tsunamis, and extending our understanding far beyond the era of modern instruments. This long-term perspective is essential. It reveals patterns that short-term observations cannot capture, such as cycles of stress build up and release, or changes in behavior over centuries. The Tonga Trench, in this sense, acts like a geological memory, storing clues about how often major events occur and how powerful they can be. There is also a humbling lesson embedded in this research. The ocean floor does not announce its movements. It shifts silently, accumulating stress without any obvious warning signs at the surface. Calm seas do not mean a calm planet. The energy that drives earthquakes and tsunamis builds quietly, hidden beneath kilometers of water, until it reaches a breaking point. By studying trenches, scientists are learning to read these subtle signals. Yes, to interpret the quiet language of a moving seafloor. Each measurement, each model adds to a growing understanding of how Earth releases its internal energy and how those releases affect life on the surface. In the end, trench research reminds us that the ocean is not just a backdrop for storms and waves. It is a dynamic interface between water and a restless planet. Even when it looks calm enough to nap on, the seafloor below is stretching, bending, and preparing for its next move. Understanding that hidden motion is not just a scientific achievement. It is a vital step toward living more safely on a planet that never truly sits still. At the bottom of the Tonga Trench, the landscape does not resemble the smooth, featureless plain people often imagine. Instead, it is a world of folds, ridges, slumps, and warped layers that look less like a simple seafloor and more like a crumpled blanket frozen in place. These strange geological formations are not random. They are the physical result of immense forces acting on soft materials over very long periods of time. Sediments arrive in the trench continuously, settling out of the water column and accumulating on the seafloor. Over years and centuries, these fine particles build up in layers, each one representing a slightly different moment in Earth's ongoing story. On their own, these layers would form neat, horizontal stacks. But the trench is not a quiet shelf. It is an active geological environment, and those layers rarely stay flat for long. As tectonic forces bend the seafloor, the sediment layers respond by deforming. They fold, tilt, and sometimes fracture, creating complex structures that can be seen in sonar images and sediment cores. These deformations are slow and subtle, unfolding over thousands of years, but their cumulative effect is dramatic. What began as simple mud becomes a contorted record of stress, motion, and time. One common feature in trench sediments is the presence of folded layers. These folds form when sediments are compressed from the sides, squeezed like a stack of papers pushed against a wall. The resulting shapes can range from gentle waves to tight, accordion-like bends. Each fold captures a history of pressure, revealing how forces have shifted and changed direction over time. Another striking formation is the slump. When sediments become unstable, often due to steep slopes or added weight, large sections can slide downslope in slow-motion collapses. What these slumps leave behind chaotic layers where the original order is scrambled. To a geologist, these messy sections are incredibly valuable. They mark moments of instability, recording episodes when the trench environment changed suddenly. Over time, these slumps and folds stack atop one another, creating a complex three-dimensional puzzle. Reading this puzzle requires careful analysis. Scientists examine grain size, layer thickness, and deformation patterns to reconstruct the sequence of events that shaped the trench. It is detective work conducted at a geological pace, where each clue may represent centuries of history. What makes trench formations particularly informative is their isolation. The deep environment is shielded from many surface processes that can erase or blur geological records. There is no weathering from wind or rain, no plant roots breaking apart layers. Once sediments settle and deform, they are largely preserved. This makes the trench an exceptional archive, storing information that might be lost elsewhere. Some formations also reveal interactions between sedimentation and tectonics. As the seafloor bends, new space opens for sediments to fill, altering how layers accumulate. In some areas, sediments thicken dramatically, while in others, they thin or are eroded. These patterns help scientists understand how the shape of the trench has evolved and how material moves within it. Even the smallest details matter. Tiny faults slicing through sediment layers can indicate subtle shifts in stress. Gradual changes in layer composition can reflect variations in material supply from the surface. Together, as these details form a narrative that stretches back far beyond human observation. There is something deeply poetic about this process. The trench does not speak in words or images, but in textures and shapes. Its diary is written slowly, one layer at a time, with every fold and fracture marking a chapter in Earth's story. Unlike written records, this diary cannot be edited or erased. It simply accumulates, patiently waiting for someone to read it. Studying these formations also forces scientists to think in unfamiliar timescales. Events that feel ancient to us may occupy only a thin layer of sediment. Entire civilizations can rise and fall within a few centimeters of mud. The trench compresses history, stacking it vertically and reminding us how brief our moment is in the context of a restless planet. In the end, as the strange geology of the Tonga Trench is not just about rocks and mud. It is about memory. Every fold, every slump, every warped layer is a record of motion, pressure, and change. The trench keeps these records without commentary or judgment, quietly preserving Earth's past beneath kilometers of water. And for scientists willing to read the diary written in mud, it offers one of the most detailed and honest accounts of how our planet has shaped itself over deep time. Deep within the Tonga Trench, life does not just endure extreme conditions. It operates under them with biochemical confidence. Every organism down there runs on molecular machinery that would malfunction instantly at the surface. And that fact has scientists paying very close attention. The trench is not just an ecosystem, as it is a laboratory full of biochemical tricks that evolution has been perfecting for millions of years. At the heart of this fascination are enzymes, the proteins that drive nearly every chemical reaction in living cells. On the surface, enzymes are picky. They work best within narrow ranges of temperature and pressure. Push them too far, and they unravel, losing their shape and their function. In the trench, however, enzymes have adapted to thrive under crushing pressure and near-freezing temperatures. These molecules do not just tolerate extreme conditions, they require them. Pressure affects enzyme structure by squeezing molecules closer together, altering how atoms interact. Surface enzymes cannot handle this. Their active sites deform, reactions slow, and metabolism grinds to a halt. Trench organisms solve this problem by producing enzymes with flexible structures that remain functional even when compressed. It is like designing a lock that still works when the entire door frame is being crushed inward. Temperature adds another layer of complexity. Cold environments slow chemical reactions, threatening to stall life entirely. Trench enzymes compensate by being exceptionally efficient, catalyzing reactions rapidly, even at low temperatures. They are finely tuned tools, capable of maintaining life's chemistry under conditions that would turn our own enzymes into useless lumps. These adaptations are not limited to a single species or group. Microbes, invertebrates, and fish all rely on pressure-resistant biochemistry. Each lineage has arrived at its own solutions, creating a diverse library of molecular strategies. For scientists, this diversity is a treasure trove. Every enzyme tells a story about survival at the edge of possibility. Researchers are particularly interested in how these enzymes might be used beyond the trench. Industrial processes often involve high pressures, low temperatures, or both. Enzymes that function naturally under such conditions could revolutionize manufacturing, making reactions more efficient and less energy intensive. It is not hard to imagine a future where trench-inspired biochemistry improves everything from pharmaceuticals to food production. There is also interest in medical applications. Understanding how proteins remain stable under pressure could offer insights into protein folding and misfolding, processes that play roles in various diseases. The trench organisms have effectively solved problems that human biology still struggles with. They did it not through design, but through relentless evolutionary trial and error. The humour here writes itself. These creatures could likely survive inside a pressure cooker that would obliterate our kitchen appliances. Put a trench enzyme in a blender, and it might politely ask for more pressure. Our technology fails dramatically under conditions that these organisms treat as perfectly normal. It is a humbling comparison, and a reminder that nature often outperforms engineering when given enough time. Extracting and studying these enzymes is no simple task. Trench organisms cannot be easily brought to the surface without damaging their proteins. Scientists must carefully preserve samples or recreate trench-like conditions in laboratories to study them properly. It is a delicate process, requiring creativity and precision to avoid destroying the very adaptations being investigated. Despite these challenges, progress continues. Each newly characterized enzyme expands our understanding of how life can function under extremes. These discoveries also inform broader questions about the limits of biology. If enzymes can adapt to such intense pressure and cold, what other conditions might life tolerate elsewhere in the universe? The trench offers clues without requiring a rocket. There is also a philosophical angle to this research. Enzymes are among the most fundamental components of life. By studying how they adapt, scientists gain insight into the flexibility of life itself. As the trench suggests that biology is not fragile or narrowly constrained. It is robust, inventive, and remarkably persistent. In the end, the biochemical secrets of trench organisms remind us that evolution is the ultimate problem solver. Given enough time, it can refine molecules to operate in environments that seem utterly impossible. The Tonga Trench is proof of that creativity, a place where life's chemistry has been pushed to its limits and emerged stronger for it. So while our kitchen appliances shudder at the thought of pressure and cold, trench organisms carry on without complaint, their enzymes humming along happily in the darkness. They are living demonstrations that life's potential extends far beyond our comfort zone, quietly suggesting that the boundaries we imagine are often just the ones we have not yet learned how to cross. Reaching the bottom of the Tonga Trench is not just difficult. It is unforgiving in a way that leaves no room for error. Every piece of equipment sent down there must survive conditions that actively want it to fail. The reason submersibles capable of visiting such depths are rare is simple. The ocean applies pressure with absolute consistency and zero mercy. One weak point, one miscalculation, and the mission ends in an instant. The first challenge is structural integrity. At trench depths, pressure is so immense that even thick metal walls can buckle if they are not perfectly designed. Submersibles are typically built with spherical pressure holes because spheres distribute force evenly. Flat surfaces or sharp corners are invitations for collapse. The design philosophy is less about elegance and more about survival. And if it looks like a floating steel bubble, that is because it needs to be. Materials must be chosen with obsessive care. Metals that perform well at the surface can behave unpredictably under extreme pressure. Even microscopic flaws can propagate into catastrophic failures. Every weld, every joint, every bolt is inspected and tested repeatedly. Engineers lose sleep over fractions of a millimeter because at depth, fractions matter. Then there is the problem of windows. Humans, understandably, like to see where they are going. But transparent materials strong enough to withstand trench pressure are rare and expensive. Acrylic and specialized glass are used, shaped into thick, curved forms that can resist collapse. These windows are not there for sightseeing comfort, and they are there because removing them would make the vehicle heavier and more complex to operate. Even so, every window is a calculated risk. Electronics present another layer of difficulty. Pressure alone is not the only enemy. Cold temperatures and long deployment times can disrupt circuits, drain batteries, and interfere with sensors. Electronics must be sealed, insulated, and sometimes immersed in special fluids that equalize pressure. It is a strange reality where devices are safer when filled with liquid than when left dry. Communication is also a challenge. Radio waves do not travel well through seawater, especially at depth. Submersibles rely on acoustic signals to communicate with support ships, sending and receiving information through sound. This method is slow and limited, turning conversations into a series of delayed pings. As if something goes wrong, help is not just far away, it is effectively out of reach. The cost of all this is enormous. Designing, building, and maintaining trench-capable equipment requires years of work and millions of dollars. Each dive represents a significant investment, and there are no guarantees of success. Weather, mechanical issues, or unexpected conditions can cancel missions at the last minute. When a dive does happen, everyone involved is acutely aware that there are no second chances. Uncrewed landers offer a partial solution. These robotic platforms can be dropped to the trench floor to collect data and images without risking human lives. Even then, the engineering challenges remain daunting. A lander must survive impact with the seafloor, operate reliably in darkness and pressure, and then either transmit data back or return to the surface intact. It is a tall order for a machine that spends most of its time being crushed. Every mission is a calculated gamble. Engineers test models, run simulations, and conduct pressure chamber experiments. But nothing perfectly replicates the real environment. When a submersible descends, there is a moment when everyone involved holds their breath, waiting for confirmation that systems are still functioning. The phrase, "please do not implode," may not appear in official documents, but it is definitely felt. Despite these challenges, scientists keep pushing forward. The desire to explore, to observe, and to understand outweighs the risks and costs. Each successful dive expands our knowledge and proves that the engineering is possible. Each failure, while painful, provides lessons that improve future designs. There is also a quiet courage in this work. Whether piloted or robotic, trench exploration requires trust in design, preparation, and teamwork. It is a collaboration between human curiosity and technological resilience, both tested by an environment that does not care about either. In the end, sending equipment into the Tonga Trench is an act of controlled defiance. It is humanity saying, "We know this is difficult, but we are going anyway." Every dive is a reminder that exploration is rarely easy, often expensive, and occasionally terrifying. But when the data comes back, when images emerge from the darkness, it proves that even in a place where the ocean would love nothing more than to crush our machines into scrap, careful design and stubborn curiosity can still win the day. At some point, scientists collectively realized that asking humans to personally visit the deepest parts of the ocean was both inefficient and deeply rude to human biology. The solution was obvious: send robots instead. Robots do not need oxygen, do not panic in total darkness, and do not mind being crushed by forces that would turn a person into a very brief news headline. In the Tonga Trench, robotic missions have become the preferred way to explore, observe, and collect data from a place that strongly discourages visitors with fragile skeletons. Modern trench robots fall into a few main categories, each designed for a specific role. There are landers, which are essentially free-falling laboratories. They are dropped from ships, sink for hours through the water column, and land on the trench floor with the grace of a well-engineered brick. Once there, they turn on cameras, sensors, and sampling devices, quietly doing science while the surface world goes about its business completely unaware. These landers are built with simplicity in mind. Fewer moving parts mean fewer opportunities for failure. They often rely on timed releases or acoustic commands to drop weights and return to the surface after completing their mission. It is a clever system that minimizes risk. Stay still, collect data, come back alive. It is the robotic equivalent of "do not touch anything, just observe." Then there are remotely operated vehicles, tethered to ships above by long cables that provide power and communication. These machines offer more control and flexibility, allowing scientists to maneuver cameras, manipulate objects, and explore specific features. The downside is that tethers at extreme depths are heavy, complex, and expensive. Every meter of cable adds weight and potential complications, turning deployment into a carefully choreographed operation. Autonomous underwater vehicles take a different approach. These robots are programmed in advance and operate without real-time human control. They navigate, collect data, and make decisions based on onboard software. Autonomy is especially valuable in the trench, where communication delays and limitations make constant supervision impractical. Once released, these robots are on their own, quietly executing instructions in a world of pressure and darkness. What makes recent robotic missions particularly powerful is the range of sensors they carry. High-resolution cameras capture images of the seafloor and its inhabitants. Chemical sensors analyze water composition. Pressure and temperature instruments record environmental conditions with incredible precision. Some robots even collect biological and sediment samples, sealing them carefully for return to the surface. Each mission brings back a flood of information from a place that was once completely inaccessible. There is also a growing emphasis on long-duration deployments. Some landers are designed to remain on the trench floor for extended periods, monitoring changes over time. This allows scientists to observe slow processes that short visits would miss. Subtle shifts in chemistry, biological activity, or physical conditions become visible only through patience, something robots have in unlimited supply. One of the most impressive aspects of these missions is reliability. Robots sent into the Tonga Trench are expected to function perfectly on the first try. There is no option for quick repairs or second attempts. Engineers test systems extensively before deployment, simulating pressure, cold, and time. When the robot finally descends, it carries not just instruments, but the accumulated confidence of countless tests and revisions. Of course, things still go wrong. Robots get stuck, fail to return, or stop transmitting. When that happens, the loss is not just financial, it is emotional. Each robot represents years of work and a rare opportunity to explore a hidden world. But even failures contribute to progress, highlighting weaknesses and inspiring better designs for the next mission. There is something endearing about the bravery we project onto these machines. We describe them as venturing into hostile environments, enduring crushing pressure, and staring into the abyss. In reality, they feel nothing. But the language reflects our appreciation for what they enable. Robots go where we cannot, and in doing so, they extend human curiosity into places that would otherwise remain unknown. These robotic explorers are also changing how science is conducted. Instead of brief, risky expeditions, researchers can now plan systematic studies, comparing data across missions and locations. The trench becomes less of a mystery and more of a place that can be revisited, monitored, and understood over time. In a way, robots have become our ambassadors to the deep. They carry our questions, our instruments, and our hopes into the darkness, returning with answers etched in data and images. While humans politely decline personal invitations to the bottom of the Tonga Trench, our machines accept without hesitation, diving straight into the pressure and silence. And thanks to them, the deepest parts of the ocean are no longer unreachable. They are just very far away, quietly waiting for the next extremely brave robot to drop in and say hello. For much of scientific history, the limits of life felt comfortably defined. Life needed sunlight, or at least warmth, moderate pressure, and a steady supply of energy. Venture too far beyond those boundaries, and biology was expected to politely bow out. The Tonga Trench did not just nudge those assumptions, it shoved them off a cliff and kept going. Every expedition into the trench has delivered the same unsettling message. Our definitions of habitable were shaped by surface life, not by life itself. The deep sea operates on an entirely different set of rules, and life has adapted to those rules with unsettling ease. Crushing pressure, total darkness, extreme isolation, and limited food are not deal breakers. They are design parameters. One of the most important shifts in thinking comes from realizing that life does not need comfort. It needs consistency. The trench provides an environment that is harsh, but remarkably stable. Temperature barely changes. There is no day or night cycle. no seasons, no storms. For organisms adapted to it, this stability outweighs the brutality. Life thrives not because the conditions are gentle, but because they are predictable. The trench also challenges the idea that energy must be abundant for ecosystems to persist. Instead of lush growth fueled by sunlight, as the deep sea shows us systems built on efficiency, energy trickles in slowly, and life responds by slowing down, conserving resources, and wasting nothing. Growth is measured, movement is deliberate, survival favors patience over speed. Another assumption quietly dismantled by trench discoveries is that complexity requires abundance. The ecosystems found in the deepest parts of the ocean are not simplistic or barely hanging on. They are organized, interconnected, and resilient. They include predators, scavengers, recyclers, and specialists, all operating within tight constraints. Complexity, it turns out, does not need excess. It needs balance. There is also the uncomfortable realization that life can adapt to conditions that actively destroy human technology. Pressure levels that crush steel, cold that freezes machinery, and darkness that defeats vision are shrugged off by organisms whose biology evolved to expect nothing else. Life did not adapt to these extremes reluctantly. It embraced them. These discoveries force scientists to rethink what extreme even means. From the perspective of trench organisms, the surface world is chaotic and hostile. Rapid temperature changes, intense radiation from sunlight, and constant disturbances would be dangerous. The deep sea is calm by comparison. Extreme is relative, and the trench reminds us that our viewpoint is not universal. The weirdness of trench life also expands our understanding of evolution's creativity. When familiar solutions fail, evolution does not give up. It improvises. Flexible bodies replace rigid structures. Slow metabolisms replace fast ones. Chemistry replaces sunlight. Yet the trench is a showcase of alternative strategies, many of which would seem impossible if we had not observed them directly. This has profound implications beyond Earth. If life can adapt to the Tonga Trench, then environments once dismissed as sterile elsewhere suddenly look more promising. Cold, dark, high-pressure worlds are no longer immediate no-go zones. The trench teaches us that life is not fragile glass. It is more like clay, reshaping itself to fit whatever mold the environment provides. Perhaps the most humbling lesson is how incomplete our understanding still is. Every time scientists think they have found the edge of possibility, life shows up beyond it, waving casually from the darkness. The trench is not an exception, it is a pattern. Our Earth keeps revealing forms of life that rewrite the rules just as we think we have finished writing them. There is also a philosophical shift that comes with these discoveries. Humans often see themselves as the pinnacle of adaptability, capable of surviving in deserts, polar regions, and space stations. The trench quietly disagrees. It shows us environments where humans are utterly helpless, yet life flourishes. Adaptation is not about intelligence or technology. It is about fit. In the end, the Tonga Trench reminds us that Earth is not a delicate planet balanced on the edge of habitability. It is a robust, stubborn world that supports life in places we once considered absurd. The resilience of life in the trench is not an anomaly. It is a feature of a planet that has been experimenting for billions of years. So when scientists talk about the weirdness of trench life, it is not just fascination, it is respect. Respect for a biosphere that refuses to stay within the lines we draw for it. The Tonga Trench stands as a quiet rebuke to our assumptions, whispering from the depths that life's limits are not where we thought they were, and that Earth, in all its crushing, lightless weirdness, is far more capable than we ever imagined. When scientists look at the Tonga Trench, they are not only studying Earth, they are rehearsing for encounters with environments far beyond it. The trench serves as a natural test case for life, under conditions once thought incompatible with biology. By understanding how life thrives in this crushing, lightless world, researchers gain a template for imagining how life might exist on other worlds that seem equally hostile. Yet one of the biggest lessons from trench research is that sunlight is optional. For a long time, the search for life focused on planets and moons bathed in starlight, where photosynthesis could occur. The deep ocean changed that perspective. Life in the trench runs entirely without light, relying on chemical energy instead. This realization expands the list of potential habitats beyond warm, sunlit surfaces to include dark subsurface oceans hidden beneath ice. Icy moons in our solar system have become especially intriguing in this context. Beneath their frozen crusts, some are believed to harbor vast liquid oceans in perpetual darkness. On the surface, these worlds look lifeless, locked in cold and ice. But the trench teaches us that appearances are misleading. If life can function in Earth's deepest oceans, then a hidden ocean elsewhere becomes a serious candidate for biology. Pressure is another parallel. The oceans beneath icy crusts are expected to be under immense pressure, similar to or even greater than that found in Earth's trenches. Trench organisms demonstrate that pressure alone is not a barrier to life. Instead, life adapts at the molecular level, adjusting membranes, proteins, and metabolic pathways to function under compression. This opens the door to life existing in environments that once seemed physically impossible. The trench also reframes how scientists think about energy sources. On the surface, energy is abundant and obvious. In the deep sea, it is scarce and subtle. Life survives by exploiting chemical gradients, slow reactions, and minimal inputs. This model is directly applicable to extraterrestrial oceans, where energy is likely limited but steady. Life does not need a feast. It needs a reliable trickle. Studying trench ecosystems helps scientists identify what signs of life might look like elsewhere. Instead of forests or oxygen-rich atmospheres, the clues could be chemical imbalances, unusual concentrations of certain compounds, or localized energy flows. The trench teaches researchers to look for subtle fingerprints rather than dramatic signals. There is also an important lesson in humility. Before deep-sea exploration, many scientists doubted life could exist at extreme depths. Those doubts were based on incomplete data and surface-centric thinking. The trench corrected that bias. Now, as scientists consider extraterrestrial environments, they approach them with fewer assumptions and more curiosity. While trench research also influences how future missions are designed. Robotic explorers developed for the deep ocean inspire technologies for exploring alien oceans. Autonomous navigation, long-duration endurance, and pressure-resistant systems are equally valuable on distant worlds. In many ways, every trench mission doubles as a rehearsal for interplanetary exploration. The humor about Earth being a training level is not far off. Our planet offers a variety of extreme environments that simulate conditions found elsewhere. By studying them, scientists refine their questions and tools before venturing into the unknown. It is far easier to test ideas in Earth's oceans than on a moon millions of kilometers away. There is also a deeper philosophical connection. Trench life challenges the idea that Earth is uniquely friendly to biology. Instead, It suggests that life is opportunistic, emerging wherever conditions allow even the faintest foothold. If that is true here, it may be true elsewhere. The trench becomes a bridge between planetary science and biology, linking our understanding of Earth to our hopes for discovering life beyond it. Importantly, trench research reminds scientists to expect the unexpected. Life elsewhere, if it exists, may not resemble anything familiar. It may be slow, sparse, or chemically strange. The deep sea prepares us for that possibility by showing how alien life on Earth can already be. Some trench organisms look and behave in ways that would seem out of place in any science fiction story. In the end, the Tonga Trench is more than a deep hole in the ocean. It is a proving ground for ideas about life's resilience and versatility. By exploring it, our scientists learn how biology adapts when stripped of comfort and abundance. Those lessons travel far beyond Earth, shaping how we search for life in the universe. So when researchers peer into the darkness of the trench, they are not just studying mud, water, and strange creatures. They are training their minds to imagine life where it should not exist. And if aliens are out there, quietly surviving in cold, dark oceans beneath alien ice, then Earth's trenches may be the reason we are ready to recognize them when we finally meet them. For all the data collected, images captured, and samples retrieved, the Tonga Trench remains largely unknown. Scientists speak about it with a mix of pride and humility, aware that what we have discovered represents only a fraction of what is actually there. In many ways, while our understanding of the trench is still at the first few pages of the book stage, except the book is thousands of pages long and written in a language we are only beginning to decipher. The scale of the challenge is hard to grasp. The trench stretches across vast distances, with complex terrain and variations that cannot be captured by a handful of expeditions. Each mission explores a tiny patch of seafloor, leaving enormous areas untouched. It is like trying to understand an entire continent by visiting a few parking lots and declaring the job mostly done. Technological limitations play a major role in this gap. Even with advanced robotics and sensors, exploration is slow and expensive. Deployments take time, and opportunities are limited by funding, weather, and logistics. Every dive must be carefully planned, and every piece of data squeezed for maximum insight. There is no casual wandering in the deepest parts of the ocean. This scarcity of exploration creates a strange paradox. The trench is one of the most extreme environments on Earth, yet it is also one of the least studied. We have detailed maps of distant planets and moons, but only rough outlines of large sections of our own ocean floor. It is a reminder that proximity does not guarantee familiarity. The excitement comes from the sheer potential. Every unexplored area represents a chance for discovery. New species, unknown geological features, unexpected chemical processes. Any of these could be waiting in the darkness. The trench has a track record of surprising scientists, which makes the unknown less intimidating and more irresistible. At the same time, there is an undeniable awkwardness in realizing how little we know. Humanity has walked on the moon, sent probes beyond the solar system, and built instruments capable of peering back in time to the early universe. Yet much of our own planet remains unexplored, simply because it is inconvenient. The ocean, it turns out, is very good at discouraging curiosity with pressure and darkness. This incomplete knowledge has consequences. Without comprehensive data, scientists must rely on models and assumptions that may not fully capture reality. Patterns observed in one part of the trench may not apply elsewhere. Local conditions could vary in ways we have not yet imagined. Each unexplored region is a question mark that limits our confidence in broader conclusions. There is also a generational aspect to this exploration. And many of today's scientists know they will never see the trench fully mapped or understood. Their work lays foundations for future researchers who will build on partial knowledge and push deeper. The trench becomes a long-term project, one that transcends individual careers. Public awareness plays a role as well. The deep ocean lacks the immediate visual appeal of space exploration. There are no colourful nebulae or dramatic planetary rings. Instead, there is darkness, mud, and slow-moving life. Convincing society to invest in exploring such places requires storytelling as much as science, reminding people that these hidden environments matter. Despite these challenges, progress continues. Each new mission fills in small pieces of the puzzle. Advances in robotics, data analysis, and sensor technology gradually expand our reach. And the pace may be slow, but it is steady. The trench is not being ignored. It is being approached carefully, methodically, and with growing respect. The embarrassment comes from perspective. Earth is our home, and yet we know parts of it less well than distant worlds. This is not a failure of curiosity, but a reminder of how difficult true exploration can be. The ocean has always been a barrier, and only recently have we developed tools capable of breaching it. In a way, this realization is healthy. It keeps scientists humble and motivated. It prevents complacency. Knowing how much remains unknown encourages better questions and more careful research. The trench becomes a symbol of scientific humility, a place that refuses to be fully understood on our terms. In the end, the vast unexplored stretches of the Tonga Trench represent both a challenge and an invitation. They remind us that discovery is not a finished chapter in human history. It is ongoing, unfolding in places we have barely touched. The fact that so much of our own planet remains mysterious is not a failure. It is proof that curiosity still has somewhere to go, even straight down into the darkest depths of Earth. By the time you zoom back out from the Tonga Trench, it becomes clear that calling it a deep hole barely does it justice. That description makes it sound passive, like an empty space waiting to be filled. In reality, the trench is active, dynamic, and busy in ways we are only beginning to understand. It is not a void. It is a working system, constantly recording, reacting, and reinventing itself beneath kilometers of water. And everything we have learned from the trench points to one central truth. Earth is far from fully explored. The planet we think we know is, in many ways, a surface-level acquaintance. Below the waves lies an environment that operates on different rules, where pressure replaces sunlight, chemistry replaces warmth, and time moves at a pace that makes human history feel like a footnote. The trench functions as a living laboratory because it brings together so many extremes at once. Physical forces, chemical processes, and biological systems all collide there, creating conditions that cannot be replicated easily anywhere else. Each expedition, whether robotic or theoretical, reveals interactions that challenge what scientists thought they understood. It is not just that new data appears. Old ideas are forced to adapt. One of the most striking lessons from the trench is how interconnected Earth's systems really are. What happens at the surface does not stay there. Materials, energy, and signals travel downward, shaping life and geology in the deepest places. The trench quietly responds, archives, and transforms these inputs, becoming a record keeper for the planet's ongoing story. There is also a lesson in humility. The trench has a habit of exposing how incomplete our knowledge is. Each time scientists think they have defined a boundary or explained a process, new observations stretch those definitions. The trench does not cooperate with tidy categories. It blurs lines between what seems possible and what actually is. This constant surprise is what makes the trench so valuable. Predictable environments are useful, but they rarely inspire breakthroughs. The trench, by contrast, thrives on defying expectations. It reminds researchers that science is not about confirming what we already believe. It is about confronting reality, even when that reality is inconvenient, confusing, or deeply weird. The humour woven through trench research reflects this mindset. Joking about pressure, implosions, or stubborn organisms is not dismissive. It is a way of coping with the sheer audacity of a place that treats human assumptions like suggestions. Laughter becomes a bridge between curiosity and respect. As technology improves, the trench will continue to reveal more of itself. Better sensors, smarter robots, and more ambitious missions will push deeper and linger longer. Each advance will peel back another layer, revealing not a final answer, but a new set of questions. But the trench does not offer conclusions. It offers invitations. There is something reassuring about that. In a world where it often feels like everything has been mapped, measured, and catalogued, the trench stands as proof that mystery still exists. Not theoretical mystery, but physical, measurable, undeniable unknowns waiting beneath our feet. The Tonga Trench also reframes how we think about exploration. It is not always about going farther out. Sometimes it is about going deeper in. The most alien environments may not be light years away, but right here on Earth, hidden beneath familiar oceans. Ultimately, the trench reminds us that Earth is not a static backdrop for human activity. It is an active participant, constantly reshaping itself and hosting forms of life that operate beyond our comfort zone. As the planet does not reveal its secrets easily, and it does not reveal them all at once. It reveals them on its own terms. So when scientists return from studying the Tonga Trench, they do not come back with a sense of closure. They come back with a renewed awareness of how much remains unseen. That awareness is not discouraging. It is energizing. It is the spark that keeps exploration alive. In the end, the Tonga Trench stands as a reminder that Earth still has plenty of surprises tucked away in the dark. It is a place that challenges, humbles, and occasionally mocks us, all while quietly expanding our understanding of the planet we call home. And if Earth is still flexing secrets like this beneath our oceans, then one thing is certain. We are nowhere near done discovering what kind of world we are actually living on.